Okay, so it looks like it will just be the two of us. Okay. Can you hear me? Yeah. Okay. Okay. Yeah, so at any point you can stop me if you want, okay? So today what we're going to do is to finish the classical linear model of light and matter interaction, and then see, okay, in classical case, how can we get the refraction index, the absorption coefficient of the material, and then also the dispersion feature, okay? And a little bit recap is that previously we introduced that the displacement field can be expressed as electrical field plus the polarization, and the polarization sum up the response from the matter, right? And then the way that it's connected to the microscopic picture is that the polarization equals to the number, well, the density, the charge density times the charge, and then the displacement of your molecules or atoms, okay, in response to the electrical field. So so very simple example now to kind of solve what the polarization is and what the displacement field is, and eventually, okay, in the linear case, you can write down displacement field equals, okay, is proportional to the electrical field with the coefficient constant here, epsilon r, and then we know that this is connected to the refraction index. So in this way, okay, by solving a single molecule, okay, and we assume that it's a homogeneous material, then you can kind of get from here to here, okay, and eventually solve the material response. And it's, in a way, okay, this is a linear interaction between light and matter under the classical model. And previously we said that for the charge, what you can do is that you can assume, okay, it's sitting in a potential well because it actually has a equilibrium position. Okay, it's sitting there under the classical model, right? And then in this case, you can write down the potential well that holding it. Potential well that holding it as kx squared plus right, it's a linear expansion, or it's a Taylor expansion of the equilibrium position. And then and then we say that, okay, to solve the displacement of the charge in the existence of electrical field and also inside a potential well, you know, the easy way you can do it is to write down F equal ma, right? And then last time we have already went through this, that there are multiple forces, okay? Forces coming from the potential well would just be the derivative of the potential well over position x, and then there are also dissipative force, okay, that you can kind of think of it as friction, that when your molecule, okay, is moving in response to the electrical field, it actually dissipate energy away, okay, outside the system. The energy is no longer in the electrical field and no longer in the molecule, okay. So all those in combine, then we arrive at this equation. It's also on page 4 of the note. So this part is ma, okay, ma. And then you will have minus kx, okay, that's the first term. And it looks like just like the harmonic oscillator, the spring, okay, restoring force of the spring. And then you will have a higher order term. Okay, see, I think it's I think in the note I missed a k here. Okay, if you look at page 4, there should be a k here. And then there's the dissipative force that's proportional to your velocity. You can think of it as air drag, okay, air drag. And eventually, of course, you will also have the the force add by your electrical field, right, QE. Okay, so this is M equals, well, MA equals F, right, in this form. And here are a few things that we need to kind of, to be careful about. First is that the electrical field, okay, in terms of light, right, we know that, well, previously we already solved the Maxwell equation, the wave equation. The light is actually just an oscillating electric magnetic field, right? So when you have light, your E can be written down as E naught cosine omega t minus kz. Okay, it's a typical wave function, or you can plus kz. It's the same thing, different direction. Okay, so this is your electrical field of a light, and often, okay, people write it down. You decompose that into let's use minus here. Okay. You guys all learned this in your math class. Cosine can be decomposed into exponential cosine x can be decomposed into e to the ix plus e to the minus ix. Right? You just use this equation and then decompose cosine into a 2 exponential term. Okay? And the reason that I want to do this is because when you look at this equation, you saw that, okay, there's a lot of time derivative, right? First order, second order time derivative. And you don't want to carry cosine around here, is because when you do derivative of cosine, it becomes sine, right? And then you do derivative of sine again, it becomes back to cosine. So that there is a cosine and sine, okay, they keep changing, okay, between each other. So the way that people usually do is that we calculate this term. We calculate the exponential term. And if you notice, okay, the real part of an exponential term also happen to be cosine x, right? So in reality, what people usually do is that we write down the E in terms of this part, okay, and then write down the E as this part, the first components here, and then we plus complex conjugate. Complex conjugate is to flip the sign when you have I, right? The complex number I here, okay? And then after the calculation, if you want to know the real part, if you want to know what the real electrical field is, you just take the real part of your calculation result, okay? And then you can get it. Okay. So another thing that we kind of want to drop here is that here z, the meaning of the z is actually is a direction the way the light is propagating, right? The light is propagating. It's perpendicular to your direction of your electrical field. So here, okay, as usually when we're calculating individual molecules, because the molecules, let's say, is sitting here and then the wave passed by. Okay, the wave passed by. then what you will see is actually the motion of the electron in the molecule is actually very, very small, right? So when you look at it, it looks like the molecule is actually at a fixed position, right? Because k is the propagation of the wave, and then this molecule is just sitting there, right? And then as long as the motion is much, much smaller than one wavelength, okay, then in the calculation you can drop the z term. Okay, you can drop the position dependence term. Okay, so here what we will have is that we'll have E is E knob, okay, e to the minus I omega t plus complex conjugate. Okay, this is what we will have. Any questions here? Okay. And then if you have more frequency components, just like in the nodes, you just add them together, right? If you have sunlight, using sunlight to do this experiment, and sunlight has lots of frequency components that have different color, okay, then you add them in the back, okay. Okay, now let's try to calculate this. Okay, we need to make a few assumptions here, just to make our life very easy. And the simplest assumption we can make is that, okay, we assume alpha is 0, right? Alpha is a high order term. Okay, when you do the Taylor expansion, it's actually the second non-zero term, and the first non-zero term gives you a harmonic oscillator, which is something really nice. Okay, so it would be nice if we first start with alpha equals 0. Okay, and then in this case, what we're doing is that we simplify the molecule into a harmonic oscillator. Okay, into a harmonic oscillator. Now then, the equation, okay, we can rewrite them. The equation become x. 2 dot means time derivative twice. Okay. Okay, 1 dot is time derivative once, and then we divide the m, okay, to divide the m left and right hand, and then we get plus k divided by m x equal to q e. Let's write this as E1. Okay. Okay, as I previously said, we can first, in a linear system, especially in a linear system, you can first calculate the, let's use omega 1. Okay. You can calculate the minus components, minus frequency components, and then if after the calculation, you just take the real part, and then you can get the solution of cosine and sine form. Okay, and one thing we want to notice here is that for harmonic oscillator, there's actually an intrinsic oscillation frequency, right? You see, the equation here is that okay, there's the intrinsic frequency is okay. What it means is that if you displace your harmonic oscillator and then you let go, okay, and then you start to oscillate at this frequency. Okay, it's just like your violin, just like your guitar. There's an intrinsic frequency here, and so what this equation really describes is that there's a molecule. It has an intrinsic oscillation frequency, but then you also have a light that's also oscillating, right? So it's like a forced motion of a harmonic oscillator. right? Itself, it has omega knob frequency, but then you also have a lie wave that try to oscillate you with the frequency omega 1. Okay, so it's a typical, very standard forced oscillation model. Okay, then we can kind of rewrite the parameters here, and replace k divided by m with omega knob, and then what you will get here is that let's see here. Yeah, let's not do that here. Okay. Eventually, what you will be doing, okay, is that you will replace k divided by m, or k, at least k, with omega knob. Okay. And the reason for this is that for a real molecule, for a real material, it's very difficult to actually measure what k is. Right? It's very difficult to measure what k is. You can't go in there and then probe the molecule and then let it oscillate for free. It's very difficult to do that. But later we will see, okay, omega knob is something that you can measure with light. Okay, measure with light with very high precision. And then m is just the mass of the molecule, and then you can also kind of get that. Okay, so with this equation, and with the understanding that this is a forced oscillation, we can expect the solution. Xt, okay, to be x1 e to the minus I omega 1t. Right? If you take a look here, on the right-hand side, you have exponential minus I omega t. Okay, the right-hand side is oscillating at this frequency. And the only way that this equation can have a steady solution, meaning that the left-hand side always equal to the right-hand side, is that your left-hand side also has to have this oscillation term, right? Every every term here, you have to have an oscillation. Okay, this way you can cancel the left-hand side and right-hand side. Okay, this is the way to do it. And so you plug this back in here, and then what you will get is, okay, twice derivative, and then I omega 1 come out twice, so you have minus omega 1 square, okay, x1. And then we neglect e to the minus I omega 1 here is because they will get cancelled. Okay, they will get cancelled left and right. Okay, and then plus here. One derivative, so it's minus I omega 1 gamma divided by m. Okay, and then x1. Okay, and then here is quite straightforward. K divided by m. K divided by m is omega knob square, right? So it's omega knob square, and then x, x1. And then on the right-hand side, you have q e1 divided by m. Okay, so now this becomes a very simple equation that you can solve, right? You just, there's a bunch of coefficients in front of x1. You just move them to the right, and then you get your x1. So the answer to this would be x equal to, okay, q e1 divided by m, okay, this part, divided by, see here, omega naught square minus omega 1 square, okay, so, and then there's a minus I omega 1 gamma divided by m. Okay, and then e to the minus I omega 1t, right? This is the x, right? And you can also write it down in a different form, which you will see. You can combine E1 with E minus I omega 1t, is because that's your electrical field, okay, in the first place. All right, so you will have Q divided by M omega naught square minus omega 1 square minus I omega 1. Okay, and this is your E. Okay. So if you look at it, what we really got here is the relationship between X and E, right? Between your motion of the molecule and your electrical field, right? And this is exactly what we want, right? Because here X is the R here, and then by multiplying with the N and Q, you actually will get the polarization of your material. And with the polarization, and then using these two equations here, you can actually get the refraction index. Okay, so let's do that. We'll have do that here. So we'll have P, okay, equal to NQ R. R is X here. And because we have assumed that all the molecules are the same, right? So the expected, so the averaged expected position motion is the same as your single molecule solution. Okay, it's not always the case, but for simplicity, we can do it here. And then you just plug in all this, so it's N Q squared divided by M. Okay, omega naught squared minus omega 1 squared minus I omega 1 gamma M, okay, times E, times your electrical field. Okay, so we now get a linear relationship between P and E. Okay, this is your, this term here is your coefficient, linear coefficient. And we pronounce this as chi. Okay, this is chi. So usually people write it down as, there's a missing epsilon here. So epsilon chi E. Okay, epsilon chi equal to this thing here. Okay, this thing here. So now if you plug this in back to D, okay, then your D equal to epsilon 1 plus chi E, right? And then in the linear region, what you also have is your D equal to epsilon R E, right? So now it becomes very clear in the linear region, epsilon R equal to 1 plus chi equal to refraction index square, right? Refraction index square. So apparently, okay, let's write it down here. Okay, let's write it down here. The complete expression. Okay, N square refraction index equal to 1 plus NQ square M omega naught 1 minus I omega 1 gamma divided by N. Okay, so this is your refraction index of the material in the classical model. Okay, any questions at this point? Okay, no, then I will erase this part, and then we're going to. I think let's see. I think I missed a term here, right? Chi equals to this relationship divided by epsilon naught. No, it actually looks good. way. I think there's an epsilon naught here. Okay, so this way, when this multiply back, epsilon naught cancel each other, and then you get this relationship. Okay, yeah, there's an epsilon naught here. Now let's look at this equation and see how it actually helps us, okay, to understand the three major observations of light and matter interaction in linear regime. So first, refraction index. Okay, it's very clear. Your refraction index is no longer 1, right? It's no longer 1. Okay, and what's the actual value? You calculate this. Okay, and then you can try this, but then from the past experience, is that actually the classical model is not very accurate. Okay, so if you plug in, okay, for example, you want to calculate water, and you plug in this, it actually won't work very well. Okay, so refraction index, it gives you a kind of understanding of this. Okay, and let's skip absorption. No, actually, we need to talk. Let's skip absorption first and talk about dispersion, right? Dispersion. You can see that here, omega 1 is the frequency of your input light, right? Your input light frequency is omega 1. And it's actually in this expression. Okay, so very simple, very intuitively, what you can see is that the refraction index, okay, has a dependence on your incident light frequency or incident light wavelength, right? And this is exactly the definition of dispersion, right? Your refraction index change with your wavelength. Okay, so we kind of have this. And now let's look at absorption. Okay, at the first look, it's kind of unclear, okay, where the absorption could come from, but something that could always alarm you is that somehow there's a imaginary term here, okay, in your refraction index. And this is something that probably you guys haven't seen in the past in your EM field. But this is something very, very easy to understand. What we can do is that we can borrow this equation, okay, in your light propagation. You can describe your light propagation in terms of omega t, and then this is frequency oscillation, and this is spatial propagation, kz, right? And then we know k. I think we say this in the first week. K equals 2 pi n is refraction index divided by lambda. Right? Lambda is a wavelength. Now suppose we have imaginary term in the refraction index. Then what we'll have is 2 pi, let's say n real part, divided by lambda. This term is kind of the same as what you used to do. And then let's say there's imaginary term, 2 pi I imaginary term divided by lambda, right? And now you plug this back into your wave propagation term. Wave propagation, your electrical field. Then what you will have is that you will always have E knob, e to the minus I omega t, okay, this is the same, and plus 2 pi n real term, okay, z divided by lambda. This term is, as usual, okay, similar. And now you have imaginary term and then the complex term. The imaginary I, okay, multiply with this I and become a minus 1, right? So what you will have is that you will have a term that's exponential. I become minus 1, so minus 2 pi n refraction, okay, imaginary number, lambda times z. Okay, lambda times z. So look at it, okay, this part is the same as before, as if the refraction index is a real number. And this term is the new term that arises because your refraction index now can be a complex number. And if you look at it, okay, you will see very interestingly, if the imaginary term is larger than 0, okay, if the number here is larger than 0, then this is actually an exponential decay. Okay, this is exponential decay with Z, and then this is the intensity, the electrical field. Okay? So the imaginary term actually corresponds to the absorption of your light. Okay, absorption of light, your light exponentially decay. Okay? And this is kind of understandable if you look at where the term actually comes from. A term showed up, okay, the imaginary term showed up because you have a non-zero gamma here, right? You have a non-zero gamma. And we said that this gamma term is a dissipative term where because of friction or air drag or, well, similar to those, okay, but it's in the molecule, that your molecule is dissipating energy from the molecule to the external environment, right? So this exact term, okay, tells you that the energy, okay, is your system is losing energy, okay? So in that sense, okay, why would that translate into absorption? Is that the energy, okay, the oscillation energy of the molecule here, the charge here, actually get its energy from the light, okay? And then when it can return that energy to the light, instead it dissipates to other system, then, you know, if you look at it overall, then it becomes absorption of the system, okay? And most of the time, this absorption will transfer into heat, okay, into heat. And that's why if you focus the light on, you know, focus light really, well, just touch the light bulb, okay, and then you actually feel the heat. So we have absorption here as well. Now let's look at something kind of interesting, okay, kind of interesting. There are a few requirements, okay, with this model, there are a few requirements that we need to hit here. One is that this should be absorption, right, because there's no external energy providing to the system. What that means is that the imaginary part of your refraction index should be larger than 0, okay, regardless of your frequency, regardless of your input frequency of light. And you guys can check that by yourself, and then it actually work. The second thing here is that we've learned in the past that light will slow down, okay, in media, right? Light will slow down in media. So what that means is that the real part of the refraction index, okay, that contribute to your wave vector, okay, wave vector should be larger than 1. Larger than 1, right? If it's smaller than 1, then the speed of light in the media will surpass the speed of light in vacuum, and then someone will tell you, okay, Einstein says that's not possible. Now let's look at this equation and then think again whether that's really possible or not, right? So when we try to discuss the real part of the refraction index, it's actually quite convenient to drop the imaginary part, right? Just say that, okay, we're dealing with something that's highly transparent, for example, glass, and then the absorption, okay, it's minimum, so that you don't care about this term. Then in this case, in this limit, okay, lossless limit, your refraction index square is actually equal to this. is equal to this. It's very easy to compare it with 1, right? Because you already have 1 here. Okay, and when you look at it, you immediately see, okay, there's a problem. The term here, following 1, it's not automatically positive, right? It's not automatically larger than 0. You will see that when omega 1 is larger than omega 0, this term actually turns negative, and then your refraction index will be smaller than 1. Okay, will be smaller than 1. So what does that mean? Well, based on what we learned in high school, it means that your speed of light in that meteor, okay, is larger than the speed of light in vacuum. Okay, speed of light in vacuum. And does that ring a bell, or does that look fine to you guys? Do you guys think the refraction index can be do you guys think that the speed of light in a meteor can be actually faster than the speed of light in vacuum? You don't think so? Mm-hmm. Yeah. So you think that there's something wrong with the classical model? Is that what you're saying? Yeah. Mm-hmm. Yeah, that's a very good guess. But in this case, it's the opposite. Actually, I'll show you. Okay, the speed of light you derive here actually can be larger than the speed of light in vacuum. Okay, and the reason is, if you really look at it here, what is this speed of light? Okay, when we say the light, when we think about light, there are actually 2 components inside. Let's say we send out a pulse of light, and then you detect. So usually the way that we measure speed of light, okay, in the past, is that you send out a piece of light, an envelope, right? And then you leave this position, okay, at this time, and then it goes to another position, and then when you detect that, okay, you clock the time, and you divide it by the distance divided by the time gives you the speed of light. Okay, so in that case, what we actually measure is the speed of light, the speed of the photon, or the speed of the energy wave pack. Right? You have to receive some energy to be able to detect the light has arrived at the other side. Okay, but then here, what we're calculating here, this has nothing to do with the energy propagation, right? It's simply a phase. So what it really looks like is that inside a light wave packet, not only do you have the energy propagating forward, you also have the phase propagating forward. Okay, you also have the phase propagating forward. And this phase, and the way, okay, we calculate this refraction index is exactly, okay, if you plug in, is exactly the phase velocity. Okay, it's showing you how fast the phase will propagate, phase velocity. And this phase velocity actually can be larger than the speed of light in vacuum. Okay, and that's not a problem. Why? So reason that people think the speed of light, well, nothing can go beyond the speed of light, is because, okay, in special relativity, you will see that once your speed of light is going forward, well, it's faster than your speed of the object is faster than the speed of light, then in the Lorentzian transformation, you will see an imaginary term that will tell you that you start to go backwards in time, right? And then you have you violate a lot of the common sense, that because you can't travel backwards, because then you can kill your dad, and then your dad, well, kill your dad before your dad met your mom, and then then you won't be there. Okay, so it's violate a lot of the consequence. Okay, but here the phase velocity actually doesn't contain information or energy, right? As long as your what we call this group velocity. Okay, group velocity means that the velocity of your light wave pack. Okay, the energy pack. As long as your energy pack is traveling at a speed smaller than light, even though your phase velocity is very fast, okay, it's going all the way there, but then since there's no energy, okay, you can't actually measure this phase, right? You can't actually measure this phase. So you're not delivering any energy or particle or information beyond the speed of light, okay? So this is actually a very interesting concept, that in light, okay, you have two velocities, and one is group velocity and the other is phase velocity. Okay, and then the definition, okay, you might wonder, okay, then what is the definition of group velocity, and then why don't we see it here? Okay, the reason is that when we do this calculation, we assume that if you look at the form of the light, okay, the light is already everywhere, right? The light is already everywhere. No matter what your z is, you always have an electrical field. So what we really, when we write down this, okay, what we really write down is a perfectly single frequency light. Okay, the frequency is very sharp. There's only one frequency component, and then when you do Fourier transform, you know that, okay, if your frequency is fixed at one part, then what that means is that your wave pack, okay, if this describes your wave pack in the time domain, delta t, must go to infinity. Okay, so it means that a light that with a fixed frequency, then its time components is spread out around the entire space, right? So when we write down this, actually we already eliminate the possibility of calculating group velocity because the light is already established everywhere in the space. Okay, so the way that to really calculate group velocity is to have multiple frequency components. Really write down this as a wave pack, and then show, okay, how this envelope of the wave, okay, move forward, okay, in space, and there you will show that, okay, it actually cannot go beyond the speed of light. Okay, and then one more interesting thing is that when this term become negative and become really large, that you can actually have the refraction index, okay, smaller than 0. It can actually happen. The real part of that smaller than 0. You can actually do Google, and then you will see, you can search for negative refraction index material. Okay, it's actually there, and then there's a lot of application that you can use for that. Okay, it will change the Snell's law, and then actually people, well, it will do weird thing, okay, under the Snell's law, the refraction law, and people use this to try to do try to do a new imaging system that you can actually be invisible. Okay, and so there's a lot of very interesting application on this side. Okay, any questions? Okay. So one word I will have is that so we say that, okay, this is a classical model, but then in quantum model, things are actually not that different. You're still going to calculate the displacement, the motion of your expected motion of your molecule, but using quantum mechanics. And then the rest is the same as long as you get the relationship between R and E. Okay, and then you use the same thing, and then you get your refraction index. Only with quantum mechanics, that number can be much more accurate. Okay. Now, let's move forward a little bit by moving into nonlinear regime, okay? Because linear regime is actually kind of, well, you only have that many things to study, okay? For nonlinear regime, what we say by nonlinear is that, later after this, you will see this, okay? Let's now move to nonlinear regime where alpha, okay, is not 0. Okay, alpha is not 0. So it's not a simple harmonic oscillator, but you actually have a higher order term, okay, that's doing a weird motion, okay, to your harmonic oscillator. And you are thinking, okay, let's say I want to be a little bit lazy. I would think, okay, previously we have already solved x equals x1t, which is just the number times E, right? It's proportional to your electrical field. It's a forced oscillation. So if you think about that, okay, then you say, okay, maybe the solution is the same form, but just the beta is different. Then you can do that, and then you can try this. So assume x equals beta E1 e to the minus I omega 1t. Right? You plug this back into here, and what you will get is that you will get minus m beta omega 1 square E1, okay, e to the minus I omega 1t. This is the first term here. Okay. And then let's use the, let's move these 3 terms to the left. And you have, this term is minus I omega gamma beta. Okay. Omega comes from the derivative of t. And E1 e to the minus I omega t. Okay. And then the harmonic oscillation term, okay, the kx term, this term would be plus k beta E1 e to the minus I omega 1t. Okay, so far it looks almost identical and then a little bit boring. Now let's get to this x squared term. Okay, then x squared term is plus alpha k squared, alpha k, okay, the coefficient alpha k, and then x squared is this, right? So you have beta squared, okay, E1 squared e to the minus 2I omega t. Okay, and then the right-hand side is the forced oscillation equal to Q E1 e to the minus I omega 1t. Okay, and then a critical difference. Now you can see a critical difference here is that before we can cancel out all the exponential term because they're all oscillating at the same frequency, I omega 1t. Right? But here, if you have an x squared term, okay, in your force, a nonlinear, okay, x squared is a nonlinear force, a force in your term, then you will see that this term it brings out is oscillating twice the speed as your other terms, right? It's 2I omega 1t. Okay, it's actually 2I omega 1t. And what this tells you, is that this equation, you actually can't have a time-independent solution, right? You can't cancel out all this term. The idea that beta is time-independent okay, it just doesn't work. Okay, the idea that the linear term and the linear case and nonlinear case share the same type of solution just simply doesn't work. Okay, the solution is not, you will not get a solution here. So think, okay, then if x is this, and then you get an x2 term, well, then you get a 2I omega t term, then you would think naturally, you would think, okay, how about I correct it by adding it by saying that, okay, xt, the motion, okay, one of them would be just like before, you have a forced oscillation of the harmonic oscillator, and then there's a second term, because you already see that there's a twice the frequency here. Okay, so maybe there's a second term that do twice the frequency. Okay, and then you can hope, okay, and then what you do is that you hope when you plug this back into this equation, okay, then the omega 1 term will cancel with all the omega 1 term, and then the omega 2 term, well, 2 omega term will cancel with the 2 omega term. Okay, that way it might also work. But then you quickly realize, okay, this is not true at all. It's because eventually when you have the x squared term here, when you do x squared of this, you will see that it will be x1 e to the minus 2I omega 1t, okay? And then you have x2, that's also squared, e to the minus 4I omega 1t, okay? And then you also have the mix between these two, right? It's 2I 2 x1 x2 e to the minus 3I omega 1t, right, the cross term, okay? So you start to see that, okay, this is a never-ending journey, right? You add another term, then you create two more terms, right? You create two more terms, okay? And this is what we actually call the nonlinear response, okay? Nonlinear response is that when you input a light, okay, into your media, when you input light into your media with frequency omega, right, you can see the output, okay, you can see the output, at least the polarization. The polarization will later drive this displacement field. The motion of your molecule, okay, is not linear to the motion of your light, right? What it would do is that it will actually generate twice the frequency motion, 3 times the frequency motion, and then 4 times the frequency motion, right? The frequency will actually be different. So what will really happen in nonlinear optics is that when you shine light onto a nonlinear crystal, then under the correct condition, what you can expect is that you can expect to see light coming out at different frequency, okay, at different frequency. So this is a typical nonlinear response. Very, very different from the linear case. Okay. Any questions so far? Okay. So the right way, kind of to approach this, is that there's a Taylor expansion regime. Okay, Taylor expansion regime where we say the polarization, okay, equals to NQR. Here I drop all the vector, okay, is proportional to, well, contains these terms. One is that there's polarization, okay, of the same frequency as your input light, right, as your input light. Okay, this is a linear term. And then you see that, okay, there is, 2 times the frequency, right? So there's another term, P2, e to the minus 2I omega 1t. And then there's a third term, P3 e to the minus 3I omega 1t. And then keep going, okay? Keep going. And then this is an infinite sequence, okay? And the way that you can drop it, okay, the way that you can kind of don't have to go over every sequence is that you have to assume, okay, if alpha, for example, alpha is much smaller than 1, right? Then you can kind of see, okay, this term, although it generates twice the frequency, it's actually smaller. And then you can further go in there, and then you will see, okay, this term is smaller than this is smaller than that. At some point, okay, you can drop the higher order term because their response is much weaker than what you can measure or than what you care. Okay, so this is called the perturbation. Okay, this is kind of the perturbation idea that what's not linear is very small, and then you only care about the leading term that contribute to your experiment. Okay, any questions? Okay, we have a few more minutes. I want to kind of briefly explain the relationship between the dipole, okay, the P here, and then the light you actually get, okay, the light you actually get. And it might look quite clear that your molecule X, right, that molecule is oscillating at different frequency. But how would that translate into light at new frequency? And now think about this is that what we learned from the EM field is that if you have a charge and then it's doing acceleration, deceleration, and then it will actually emit electric magnetic field, right? So now if you have a molecule, a charge, that keep oscillating at 2 omega frequency, right? It's cosine, so it's accelerating, decelerating. So this motion of the charge, okay, is going to emit photons, going to emit EM field at this 2 omega 1 frequency. Okay, so whatever frequency you have in your R, and then in your polarization, will eventually translate into electrical field. Okay, translate into light. Okay, because your charge is literally moving here. Okay, and then in the next class, what we will do is that we'll first show you guys. Let's see, can we do it right here? Okay, we can do it in the next class since one of you is going to leave at 12. So in the next class, we will kind of formalize, okay, this idea of nonlinear polarization. Okay, we'll put them into first in the classical model, and then we put that into the EM wave in the nonlinear regime. Okay, and then we'll get a kind of a master equation that you guys will need to use probably at least 50% of this class. Okay, any questions? Okay, then that's it for today. Okay, see you guys.